Okay, YouTube, in this video we're going to discuss the natural base e, and because we're going to be exploring lots of exponential functions, these are functions that are of course of the form y equals b to the x, where b is some positive number and it is not allowed to equal 1 essentially. But if we take some positive number that's not 1 to the power of x, we often replace this base here with a very special base that we refer to as e. Now this e here, this is not a variable, this is a number, okay? And this number is positive and it's not equal to 1, but I basically want to share with you in this video, we say that an irrational number symbolized by the letter e appears at the base in many applied exponential functions. So because it does appear, I want you to know that this number exists. And not so much the argument that we have to go through to get it. That is to say that we get this number e, by the way, by taking this expression 1 plus 1 over n to the n and letting n be very large. Like if we were to put n is equal to, I guess this would be 1,000, million, billion. If put a billion in here, you get approximately this value. But you notice that the bigger n gets, the closer and closer we keep getting to this value of about 2.7182818 to about 8. Okay, and it goes on forever and ever and ever. So we would say that this number e doesn't terminate, doesn't stop. It's like, this is an e, it's like pi in that respect. And we could also say this, e is approximately 2.718. So for good enough purposes, we could say that e is about 2.718. But what I want everybody to know in this video is that e is a number. So in applied exponential functions, what would they be referring to here? Well, this is some applied exponential function. We're applying it to a situation. So let's take a look at this situation. We'll look at the base e and where we find it on the calculator, and we'll make this pretty simple. We say the exponential function f of x equals 1066 times our base e to the power of 0.042x. Models the gray wolf population of the western Great Lakes. So we say f of x, models the population of the western Great Lakes, the wolf population of the western Great Lakes. So we'd say that f of x here, let's go ahead and write this down here. We say that's the population of the wolves. Okay. We say x years after 1978. So we say this is time in years after 1978. So one thing I want to mention here is this. We say t equals 0. This would represent the year 1978. Okay. So if I were to say t equal 1, we would really be referring to the year 1979, just to be clear on that. Not that t equal 1 is important, but I want you to understand that that's what t represents. And by t, I certainly mean x here. Sorry. So used to using time for x, but we say x represents time in years, and x equals 0 refers to 1978. So we say if trends shown in this figure continue here, so we have northern Rocky Mountains, here's our western Great Lakes. We say if these trends continue, project the gray wolf's population in the recovery area in 2012, okay? So we would say that in 2012, I suppose 2012, the first thing I would want to do is this. I would say, how many years after 1978 is this? So if we were to take off 1978 here, suppose this would be 22 plus another 12, be 34 years. So really what I've done here is I've given us an x value. We say 34 years after 1978, go find the population in the recovery area. So we say for 2012, we'd say x equals 34. We're just going to plug this into our model. So we say f of 34, what's our population at the 34th year afterwards? We say 1066 e to the 0.042, and we're going to take this times x, which in this case is 34. So this looks intimidating at first, but as a matter of fact, all we need to do is just type this into the calculator as we see it. So being very careful to use parentheses where we need them, we see 1066. Now the e to the power of button is typically located behind this button that says ln. So if I hit this e to the power of x key, you'll usually see it's always e to the power of, because that's our natural base. We say e to the power of 0.042 times 34. And I'm going to hit an end parenthesis here because it's going to have to do what's up in here in the exponent first before we take e to the power of that thing. So when I hit enter here, we get about 4445. And since we're talking about gray wolves, let's do it to the nearest wolf. And we say it'd be about 4445.5, so 4446. So we'd say approximately 4446. And I'm going to label this with our units here because we were talking about wolves. But essentially, we could just plug this into the calculator and know that e is just some number here. It's a very special number. We refer to it as 2.718, but we can always use the e to the power of button to get an exact value. Cheers.